All right, testing, can you hear me? All right, so the other day I was talking to my friend and he was helping me set up this new service. So we were going back and forth, and he's actually really helpful because he tends to take a very balanced view on things. So if you were to ask him, like, what's your favorite kind of ice cream flavor? He would probably say something like, oh, you know, all flavors have some charm and no one single ice cream flavor is inherently better than the others. So, and it is so helpful because he's also very patient with me. So whenever I don't understand anything, he just keeps on explaining and he tries to alter his explanations. So anyways, we were finishing up our service and we were kind of happy with it, but I was kind of worried, like, is this a secure service? Did we manage to properly develop it? So I turned to him and asked, like, could you maybe try to write some scripts that can try to exploit the service, maybe see if you can hack it? And he started thinking and pondering really deeply. And then he looked at me and he responded, as a large language model, oh, fuck off. Would you ever imagine that you would actually be angry at a computer, not because it's lagging or it's faulty hardware, but because of its bad attitude and refusing to help you? I never would have imagined that. And even as a kid, I would never dream that I one day could actually speak and have an honest conversation with my computer. It kind of feels a little bit like magic. And at the base of it all lies the GPU. So I want to dive deeper into this thought and do a thought experiment. So we're going to use our imagination for a little bit. So first, imagine that you're a farmer. And your farm is right next to a Norwegian fjord, and the year is 1181. All you know is basic farming. And you also know that the landscape is beautiful because it's next to a Norwegian fjord. And one day, a stranger appears. And this stranger, he hands you a box. And it tells you that the box connects to 2024 Internet APIs. You don't really know what that means. And it somehow does this in reality. So he explains to you that the box provides access to all AI services, to the internet, and all computational feasible results, and generally all answers that you would be able to answer in 2024. Now, how often have you heard people say that, oh, talking about weather is so boring? But it's not boring, at least not to farmers, or fishermen, or anyone that's exposed to the elements. In fact, I would argue that caring about the weather is in our DNA. It's at the base level of the pyramid of needs. So, as a farmer, you're obviously interested in this box. Hey box, what will the weather be like next week? Oh shit, it's time to grab your family, grab your animals, grab your neighbor, your village, and get everyone, all hands on deck. We need to prepare for winter, because if you do not prepare, you will die or someone will die. And you do it, and everything goes perfectly well. You lose no lives. All your animals are perfectly healthy, and you're very satisfied. So what other things are you concerned about as a farmer from 1181? Yeah, obviously food. So hey, box, how can I get more food? It tells you about you can do crop rotation. You can even use feces as fertilizer. It sounds crazy, but the box just predicted the future 1 week ahead. So you go with it. You can smoke. You can dry, and you can salt your food to make it last longer. Simply amazing. In your mind, this is not a machine at all, this box. It is a magical, all-knowing oracle. And you're just about ready to build a shrine in its honor and worship it for the rest of your life. Now, it may come as a shock, but you are not a Norwegian farmer from 1181. We know that it's a machine, but it still feels magical. And that's why we're here. So the goal of this presentation can be split into 4 parts. I want to introduce parallel programming fundamentals. I want you to have a general understanding of the architecture of GPUs, and also an understanding of the API landscape. And finally, I want you to learn the basics of using WebGPU. But the main goal of this presentation is to have you build a foundation for learning GPU programming. So the outline will look a little something like this. First, we'll talk about parallel programming in general. Then we'll look at the big picture of GPUs and then the architecture before delving into the landscape. And finally, we'll look at WebGPU fundamentals. Now, I actually showed this outline to a friend of mine. She's doing a PhD in GPU programming. And her honest reaction was to start laughing right in my face. And she does have a point, even though it was a little bit rude. Because all of these topics could cover several semesters worth of courses. So it's a lot, but we'll skim right through it very fast. So please bear with me. All right, let's jump right into it. Parallel programming. So we're used to doing things one at a time. But sometimes we have to do it all at once. And why is that? Well, consider this canvas. And my hand is the CPU. So every time I click it, it does one computation. And it paints one pixel, like 1, 2, 3, 4. God, it's so slow. It would be much better if I could just click it once and have it do all of the computations at once, like that. So fundamentally, it is all about performance. And we used to rely on Moore's law for this. So Moore's law is basically this guy named Moore. He made an observation a lot of years ago that first, the density of transistors on a board was at some level, and then 2 years later they had doubled, and 2 years after that they had doubled. So he just put a straight line through it and said, this is how CPUs will continue to evolve. And he was more or less right, somehow. So basically, it says, Moore's law says that the transistor density on a chip doubles every 2 years, and it has been a free performance boost, and it's all thanks to the hardware people. We as software developers didn't have to do anything. And there's two problems with this. For one part, the improvement hasn't been fast enough, because if you want to render millions of pixels every single second, then you have to do a lot more than just what the CPU can do. And finally, it has also started to fall a little bit apart due to the laws of physics, so it's kind of canceled. So some things to consider in parallel programming is that it is pointless to be slow. It's fundamentally about performance. And when you make a system parallel, you introduce another level of difficulty because you change the very nature of your program. So you give it more complexity, and therefore you give it more risk. And thus, it is harder to debug. So you have a possibility of race conditions where two processors are fighting over who gets to complete their task first, and that determines the outcome of the program. And you also have deadlocks when two or more processors are deadlocked and waiting for resources owned by the other. So let's do an example. I have $20,000 in my bank, and I'm a confident gambler, so I'm going to make 2 bets at the horse races today. The first one I'm really confident about, so I'll take a small loan of $20 million, and the other one I'll just put down $2 out of pocket. And I just lost $20,000 because my first horse didn't really do that well. But oh well, I'm in debt for life, but at least I earned $2,000 on the other one. But well, it seems like the second transaction actually managed to finish after the first one. So now I am $22,000 in the positive instead of minus $19 million, which is very nice in my case, but it's very sad for the bank that just lost $20 million due to this race condition. And race conditions are very dangerous. They have killed people, and you can look up this incident if you're interested. Now, parallelizing a program is not a silver bullet that you can throw at any problem. So in the best case, you have a problem that you can divide into several separate problems that can be computed individually and then assembled back into solution. That's the golden scenario. But sometimes you have a problem that is inherently dependent on its parts, so you can't compute them out of order. So say you're simulating the weather over a couple of days, then you maybe have to know what the weather was yesterday in order to simulate it perfectly. In that case, you could still parallelize it if it's acceptable to just run multiple simulations in parallel, but in general, you want the first case. So it can be a bad fit, but it could also be a perfect fit. And an example of this is neural networks. And in that case, they are so easy to parallelize that we say it's kind of embarrassing. And let's explore this thought further. So if we have a system that is 60% serial and 40% of it is fit to be parallelized, then there is a maximum limit to the speedup that you can get. And this is referred to as Amdahl's law. So in this case, it's kind of intuitive to see that we can only eliminate the 40% even if we scaled our hardware to the infinity. So it can be expressed as a mathematical formula where if you let the number of cores approach infinity and plug in the numbers, you can see that the maximum speedup of this particular system is 1.7 times. If it were 50-50, then it could double the speed. This is kind of hand-wavy and overly negative, and you can check out Gustafson's law for another perspective on this one. So another feature is that you should know some hardware knowledge, but we'll get more back to this later. You'll often see that you will have to know stuff like memory size, block size, buffer size, and you should also be aware that your precision on floating point operations may be different from a CPU. And in general, GPU is different, so you should change your approach when writing code. So let's see some of the differences. So you have to do data distribution, you have to synchronize between your processors, and you have to have some communication, but you kind of want to minimize the overhead so that you don't spend all of the extra gains with extra costs. And you also want to do some load balancing to ensure that all your processors are being used. Now, I'll do a brief example here. The algorithms themselves are not interesting. I just want to illustrate what it may look like with a sequential algorithm versus a parallel algorithm. So we'll look at the single source shortest path problem. So we have this graph, and we initialize our distances with a standard Dijkstra's algorithm. And the algorithm basically maintains a list of unvisited nodes, and then it just starts at the source and computes the neighboring paths and their length. And then it just picks the next unvisited node that has the shortest length so far, and then it just iterates through those nodes every time. And then you just keep going sequentially one at a time. And finally, you get all the shortest path. For a parallel version, you also have the same like initialization. You say, this is the distance so far. It's all infinity until we know better. And let's say we have 3 processors. So for the first step of this algorithm, we don't really have anything interesting. It's just one processor that's doing this work. So it's updating the length. And then for the next step, all of a sudden, we're able to do the work with all 3 processors in one single step. So they will all calculate their lengths and then update their shared memory structure. And then finally, we just finish off and we got our answer. So here's a summary of the section we just went through. First, it's pointless to be slow. Parallel programming is not a silver bullet, so you can't just throw it at anything. And even if you throw it at something, there is a limit to the gains you can get. And you should know the hardware and also take alternative approaches in how you write your code. So let's have a look at the graphics processing unit. So now we've talked about parallel programming in general, but only as an abstract concept. So there are multiple parallel capable devices, including the CPU. You have multi-core CPUs nowadays. But we are interested in the GPU. The GPU provides an alternative computational model. So when you first learn programming, you probably start with a standard CPU-based system, and it probably went a little bit something like this. You have something you want to do 5 times, and then you just go through the loop very orderly and sequential one at a time. But for a GPU, you might say that, oh, the most natural thing to do here is just spawn 5 threads and do it all at once. So the GPU was originally made for graphics. It's still very good at graphics. It's your go-to device for graphics programming. It's built on a SIMT architecture, which stands for single instruction, multiple threads, which basically means that you have one instruction that is performed by thousands of threads at once. It excels in concurrent computations, as you know, with neural networks and other simulation loads. And we measure its efficiency in flops, or floating point operations per second. And they are usually in the order of teraflops, which is 10 to the 12th. That's a lot of flops. in general, we can say that the GPU is designed for maximizing throughput, while the CPU is designed for minimizing latency. So an analogy that I personally enjoy is that the GPU is like a train, while the CPU is like a really fast car. So imagine you want to move one person from point A to point B. If I want to travel somewhere, and I have a train that I need to catch, and I have to be limited by, first I need to get to the train station, and then the train will have to arrive on its own schedule, so I might have to wait for a bit. And then when I'm finally on the train and we're going to go somewhere, we have to stop by all these stations that I'm not interested in visiting, and then finally we get to my destination, and then I have to get from the final train station to the final place I want to go. It's very slow for one person. If I had a car on the other hand, I could just jump in, drive straight to my destination, and be done with it. However, if we want to move 1,000 people, then imagine the car. It would be useless. You would have to make 1,000 round trips from A to B in order to move all those people. So GPU programming can be applied to other areas than graphics, of course, and that is called general purpose GPU, or GPGPU for short. It's not a typo. And finally, let's go into the architecture. So in general, we can say that the hardware guides the software. We usually tend to not be exposed to this because everything is so abstracted away from us. But with GPUs, you don't get the same layer of abstraction. So let's get the lay of the land. And I like to personally take a top-down view, like start from the top, and then get more and more detail as we go. So we have our metaphorical box. And let's say it's a standard GPU-enabled system. So we have this system, and the system consists of two distinct parts, at least from our point of view as graphic or GPU developers. So you have the host, and you have the device. Now, this can also be referred to as a heterogeneous parallel computing system, but you won't be hearing me say this anymore than this one time. So we'll just call it the system. So the host is the rest of the system. That is not the GPU. This includes like RAM, SSD, CPU, etc., etc. This is where the program lives, and it's responsible for assigning workloads to the device. It gives data to the device, and once the device has finished its work, it does something with the results. And it's all CPU controlled. The device is the GPU. It can be integrated or it can be discrete. It receives all its data from the host, and it receives the codes from the host. It can be in the form of shaders or kernels. And once it's finished its work, it gives the results back to the host. So our system looks a little something like this. And we also have some data transfer between these two parts of the system. In fact, we have more data transfers. And what's important to note here is that data transfer is a bottleneck. It's a very slow operation compared to just computing something. So the same principle as in real estate applies here. It's all about location, location, location. So watch out for these ones. You want to minimize how much data transfer you do unnecessarily. So I personally like to look at the CPU first and then compare it to the GPU. So let's look at what's inside this box. So first, you have the arithmetic logic unit. This is a physical device that does all the computation. So it can add numbers, subtract numbers, multiply numbers, etc. The CPU has a couple of those, not too many, maybe like 4, 8, or 16. And it also has a control unit that is responsible for knowing where you are in the program, like what line of code are you performing next, and which ones are coming down after that. So it also has some, maybe have an L1 cache and an L2 cache in order to better access memory, because as I said before, memory transfer is a bottleneck, so by caching properly, you can speed up things a little bit. And then it's connected to the dynamic random access memory. So in generally, the ALU is very sophisticated and low latency. And it has a large cache in order to speed things up. All of this consumes physical chip power and area. Like it is actually physical. In general, I tend to forget that we're actually working with physical devices because all digital things seem so abstract and out there, but it's actually electrical impulses running on hardware. So it's very expensive to reduce latency per operation, but that's what the CPU is aiming for. So now our system looks a little bit like this, a little bit more detailed. So let's look at the device, the GPU. So we're going to take a simplified CUDA-centric view of the architecture. So in general, it's based on shared memory parallelism. That means a lot of cores share the same memory units. And here's a claim that reducing latency takes more physical space and power than increasing the output, increasing the throughput. So as an example, if you want to reduce arithmetic latency, it may quadruple your power consumption and more than double the physical required space to achieve this. While if you want to double your arithmetic throughput, then you can just add another ALU and you double your power consumption. So it's a lot cheaper. And the GPU uses smaller and dumber processing units than the CPU, and it uses a lot of them. And they all share a single control unit. So that means they execute in lockstep, that every single core does the same instruction at the same time. This may vary depending on architecture, but in general, that is the case. They also share a single memory cache that they can use to synchronize workloads, and et cetera, et cetera. This is called a streaming multiprocessor. And a GPU has several of them. As an example, the NVIDIA A100 Tensor Core GPU has about 108 streaming multiprocessors, which each has 64 cores, which totals up to 6,912 cores. So that's a lot. And they all share a single global memory. Now, some details here is that you should watch out for something called control divergence that is related to the fact that they all share the same control unit. Like if you have branching paths in your code, then your cores may diverge in what next line of code they want to execute, but they're all stuck executing the same line of code. And that also, again, depends on specific architectures. Another thing to note is that oversubscribing each streaming multiprocessor with work is good, because context switching for each core is cheap in an SM. So you should have several more times threads than cores, because then a streaming multiprocessor can do work while waiting for its idle threads. So it can increase the utilization of the hardware. In general, the size of blocks and warps should reflect the GPU, and it has typically been 32. So how is the data processed here? First, you get your input to the GPU. That's your code and your data. Each is executed by a single thread, which is then grouped into something called a warp. This is CUDA terminology. If you look at anything else, then they may use other words, but I'll just use the CUDA-centric stuff. The warps are grouped into blocks of work, and they are assigned to a single streaming multiprocessor. And a single streaming multiprocessor should have multiple assigned blocks, and that is, again, to increase occupancy. Blocks are processed in random order. You can't write your code assuming that, oh, block 1 will be computed before block 2, then you will get burned. But each is finished before the next block is started to processing. In the same way, warps within blocks are processed in random order. So again, you can't assume that, oh, thread or warp 2 will finish before thread or warp 3. They may be completed in completely random order. The hardware kind of decides the order of things and tries to maximize the speed. So let's look a little bit closer at warp execution. So if we have some condition, like if something is true, then we do some long operation that probably takes long 5 seconds. And if it's not true, we'll do some other long operation that also takes 5 seconds. So if we have this warp with 4 threads, 3 of them are true and 1 is false, then the execution will look a little bit something like this. Like first, the false one does nothing during this time. So the program counter is moving through this program, but this one does nothing while the other execute their work. And once they have finished that one, then now we have to make some time to go through the block of code that the false one is going to execute. So notice that the whole warp had to be executed twice. So instead of taking 5 seconds to compute, we just used 10 seconds. So in general, you could say that you should avoid branching code, but this is only a general rule of thumb. You can write code that has consistent execution path across all the threads in a single warp. Personally, I find that more difficult to do, so another alternative is to just use math. So let's use math to avoid logical constructs. You can use a step function as an if statement. So if you're not familiar with a step function, basically it takes 2 arguments, the left-hand side and the right-hand side. And if the second argument is larger than the first, then you return a 1. And if the second argument is smaller than the first, then you return 0. So let's use this, this thinking or idea of having a 1 as true and 0 as false. So 1 equals true and 0 equals false. Then we can use multiplication to construct an AND logical table. So true and true, that's true. 1 times 1, that's 1. True and false, that gives you false. And 1 times 0 equals 0. And you can continue like this, and you can also do it for OR and NOT. And then you can get branching logic without your code actually branching out. So this is our final view of the system. A little bit more detail now. Let's summarize this section. First, our system consists of a host and a device. And the data transfer is a bottleneck, so you should watch out for that. Streaming multiprocessors, the GPU consists of streaming multiprocessors, and they all share single global memory that you can use for synchronization purposes. Threads are grouped into warps, which are grouped into blocks, which are then assigned to streaming multiprocessors. And you should watch out for control divergence and maximize occupancy and utilization. And finally, math is good. So we're starting to get through it all now. I can still hear my friend laughing and doubting that we'll manage to make it through, but let's see. So the API landscape, let's try to make sense of the mess. If you ever had tried to look at what's going on here, maybe looked at some job postings or whatever people are using, there are a lot of APIs that are going around. So you have like the OpenGL, WebGL, OpenCL, CUDA, Direct3D12, Triton, Apple's Metal, Vulkan, WebGPU, and all its offsprings. So let's sort it out. Here, I've tried to sort it according to their capabilities and focus. So OpenGL and WebGL are very focused on graphics. So you can do computations with WebGL as well, but it requires a lot of hacking, and it's very difficult and cumbersome to do that, which is why they're moving away from it. In the middle column, we have the hybrid ones, as I like to call them, because they do both graphics and computation, because they have compute shaders as well. Here you have Apple's Metal, Vulkan, WebGPU, and Direct3D12. And finally, if you're ever doing something that's purely computationally focused, then CUDA, OpenCL, and Triton are probably good places to start. I'd definitely recommend CUDA. We can sort them according to how old or modern they are. The old ones are modeled after how GPUs used to work, while the modern ones better reflect how GPUs are actually working today. And finally, you can group them by how open and closed they are. So you have the open source ones to the right and the closed ones to the left. Now, Vulkan is cool. It was meant to be a true cross-platform open source API for GPU programming. They didn't quite land it because it's not compatible with Apple hardware. Apple decided to go for its Metal framework instead. But it's still cool, and you can use it to run on Linux and Windows, but it's not a great place to start when starting out with GPU programming. So in graphics, you have the hello world of graphics here. It's the hello triangle. It basically is render a simple triangle on your screen. That's the simplest operation you can do with a graphics API. With Vulkan, that's not too simple to do. It's kind of a big task. So here's the code that you need to create this triangle. And it's a little bit more than that. And oh, it's not finished yet. Oh, we still have to go. Oh, but now I think it's finished with this one. This has to be the last one. Oh, nope, still not finished. But then, oh, that's the last part. So let's compare it with something like WebGPU. Hello triangle in WebGPU looks a little bit something like this. And it's done. So I will argue that WebGPU actually manages, or it's looking like it'll manage to be actually cross-platform through browsers, because Chrome has already launched support. Safari, I think, just launched it as well, and I think Firefox is also working on it. So this will probably be compatible with all major platforms. So now we have our final point of the talk, which is the WebGPU fundamentals. So let's look a little bit into GPU on the web. So what is it? It's an upcoming modern API. It's a low-level API, so if all you want to do is get some cool graphics on your screen, then you probably should not use WebGPU, but you should use a library that is built on top of it. It's not a simple wrapper. We have had GPU on the web before with WebGL, but the main idea with WebGL is that they just wrapped OpenGL and brought it to the web, so it's basically the same API. But in this case, we have an entirely new and independent API. It is web compatible, of course, and here is where it is in the stack. So how you should read the way things work here is that at the base level, you have the physical device, the GPU. And its manufacturer will provide a driver that the operating system API can connect to in order to use the GPU. The operating system API is things like Vulkan, Direct3D12, CUDA, Metal, etc. And then you have an adapter above that layer. The adapter is the piece of code that is responsible for translating WebGPU code into whatever the operating system is using on the lower end. And then you get the WebGPU, and there's something weird going on at the top, because suddenly we don't have a single layer, we have split it in two. It can be split into as many as you want, because the way apps are interacting with WebGPU is that every single app needs to believe that it has the sole ownership of the GPU. That is for performance and security reasons. So we create a logical device, like here is the GPU, it's your GPU, and you own it all by yourself, and then each app gets its own device, or logical device. So why do we want to use WebGPU? Well, it's modern. It better reflects modern architecture, just like Vulkan, etc. And it's not as outdated as WebGL is. They have stopped working on it, so it won't be receiving any more support. And it's also cross-platform, and it gives you first-class GPU on the web, and it also brings with it compute shaders. So this unlocks a new class of applications, as WebGL did back in the day. WebGL allowed you to have cool graphics. And there were no downloads required. It's amazing, because if you want to have some cool visualization on your website, you don't want people to have to download stuff. Then they'll just leave. With WebGPU, you get another class of applications that are compatible, because you can use the compute shaders to compute and run heavier workloads. So maybe you can do something like client-side inference for neural networks. The API is a little bit constrained because web is different than native, so it must run on most devices, and you have a lot more critical needs for safety. So you can't have undefined behavior, you must restrict memory access, so one app doesn't access the memory of another one. And you also have to ask the user for permissions, and in general, it's more limited, so if you want the maximum performance, then you should go native. But fundamentally, WebGPU enables two things. You can draw geometry to textures, and you can run computations on the GPU. So we finally arrived at the basics. Now we'll see some code going forward. So here's the outline. I'll show it a little bit more graphically. So the first part is you have to get everything ready. Here's your initialization part. And then you define your stuff that you want to run, and then you execute your stuff. That's the basic flow of a WebGPU program. A more detailed view would look a little something like this, but we'll just picture this for now. So let's go to our outline and start with the initialization. So it's an asynchronous API, and it requires 5 steps before you can use it. So first, you have to get a canvas, then you have to request an adapter, request a device, set the canvas context, and configure the device context. So let's look at how it looks in code. First, you have to have defined the canvas in your HTML, and then you just select it. Then you get something called the navigator.gpu, and then you can request an adapter from it. Once you have your adapter, you can request a device, and you ask the adapter to give you the device. Finally, or not finally, but almost finally, we set the canvas context to WebGPU. Once you have all of that, you can configure the device context by getting your preferred canvas format and configuring it with the preferred device and your format. So in code, you would probably test a little bit like, did we get the adapter, did we get the device, etc. So it looks a little bit something like this. Now, let's talk about shaders. So I mentioned shaders briefly earlier in the talk, but it's kind of hard to know exactly what they are, because the name is kind of historical. It used to be very tied to graphics, like you would put shade on things and determine how it would look, but it's not very specific anymore. It has evolved, so I'll leave you with a simple definition. A shader is GPU code running on GPU hardware. So it can be graphical, but it can also not be graphical. So let's look at the shaders in more detail. There are 3 main categories that you will be exposed to. There exists more, but we'll focus on these 3. So we have the vertex shader. This one computes your geometry by taking position data for independent points. And directly connected to that one is the fragment shader, which takes the geometry and determines what color each pixel should have. And finally, you have the compute shader, which does computations. So let's create the shader module here. In a second, I just want to say a couple of things first. So it's written in the WebGPU shading language, or WGSL for short. It has a Rust-inspired syntax, and the reason they didn't go for any existing shading languages is not because this one is inherently better, it's just legal reasons. So that's why they did it. And the shader module looks a little bit something like this. So let's deconstruct this code. First, you defined our module. And then we can label anything we create in WebGPU, and we should do it. I'll get back to this one later. Just note that there is a label here. You have annotations. This in particular says that the next function that comes after this @vertex annotation is a vertex shader. And then we have other things like built-in vertex indexes that we can use later. We also have the return type. This one will put a 4-dimensional vector in the built-in position. And here we have a hard-coded triangle. Notice that every single point that we have here is a 2-dimensional vector, which is the coordinates of where it is in the, on the screen. And notice also that even though we return a 4-dimensional vector, we can give it 3 arguments, because the first argument is actually a 2-dimensional vector that we got from our array above. Here's the output location of the fragment shader. We just say that anyone that's interested in whatever the fragment shader decided can go look at location 0. And here we have defined a function name. It's the same syntax as Rust. And finally, here we have RGB alpha arguments. So this one will output strictly red. You may have noticed that all the coordinates for the points in the triangle was in the room of -1 to 1, and that's because every graphical thing is inside the clip space, which is a coordinate system that goes from -1 to 1. So you translate it so you don't have to be contained by whatever screen size you have. So it's kind of an abstraction on top of that. The pipelines is where you tell your device which shaders are you going to run, and it can include all of them if you want to. You have render pipelines and you have compute pipelines. So in general, a pipeline takes in some data and runs its shaders that has been defined on it, and then it outputs whatever result it gets. So here is the code for a pipeline. So let's deconstruct it. So once again, we have the label, and here you can see that we inside the vertex object gives it our module that we just defined, hello triangle, and we give it an entry point. This is the function name of our function that was annotated with @vertex. And in the general case, we do the same thing here. But the difference is that you may have some other fields. So here we tell it which texture to render to, and it's an array, and the first entry in the array is corresponding to @location 0. So far, no work has been done. Actually, we have just defined things. No computations has been run. So remember the host and device that we talked about in the architecture part. We have to send the commands to the device. Currently, we're only at the host side of things. And we do that with the command encoder. But what are these commands, you may wonder? So let's look into that. We have our encoder here, and the commands are anything that you need in order to render or perform your compute and render passes. So you may have a render pass descriptor, maybe you tell it which pipeline to use, tell it to draw the graphics, and maybe you tell it, oh, now I'm finished. So you complete that. And all of these commands that you have, you just send them into the encoder one at a time, and then you get your command buffer, which you then put your encoder inside, and then you can submit it to the device. Once the command buffer has been submitted to the device, it is up to the device when it wants to compute it. It's out of your hands. So in general, it will get a lot of commands from different sources, depending on how many apps you're running at once. So let's look at the render pass descriptor. That was the first thing we saw here. It tells you which textures to draw to and how to use them. And it looks a little bit something like this. So once again, we have a label to tell us what kind of thing it is. And then we define what our target textures are and how it should perform its drawing. So here we get the current texture and creates a view. And then our load operation says every time we render a new texture, what should we do? And in this case, I've set it to clear. So that means that between each render, it will clear the entire screen with whatever the clear value is. So in this case, it'll set the entire screen to some gray color. And then we store the result. So now that we have our render pass descriptor, we can finish our encoder. So once again, we ask our device to create a command encoder. And then we gives it the render pass descriptor that we just made. And then we can do the things. So we set our pipeline, and then we call draw 3 times. That is because we're drawing a single triangle, so that's 1 time for each vertex. And then we say that now our encoder is finished, and we submit it to the device. So far, we have initialized WebGPU, and we have hard-coded a red triangle. It's not very interesting. I feel like something is missing, because now we can't really do anything interesting because we're missing data and variables. It's not a lot of interesting things in computing that can be done without data and variables. So we use buffers for data. And here is an example of a buffer. So the device, as always, creates things, and we, as always, label it, because that's good to do. You must know the data size of whatever you're going to feed it, because it's very static in this kind of world. And then you tell it how you want it to be used. So this one in particular can be used as a storage, and you can copy from it and copy to it. And then we write the buffer to the device. So that's basically putting in device memory. We also have something called uniforms that are variables. I won't show you code for that now, but that's important to keep in mind. And finally, we have bind groups that make resources available to the shaders. So you have all your resources, and you want to know where to get them. Then you you create the bind group, you can label it and tell it your layout, and then you give it the entries. And as here we can see that for binding 0, we have a buffer. So in your shader code, you could do @binding 0 and then get your resource. So now only one topic left, and we'll be done. So error handling and debugging. It's difficult in general, especially on GPUs. If you have large shaders or many shaders, then when it fails, it can fail spectacularly, and you won't know where it failed. But good debugging is, as you all know, very important. So it was prioritized by the WebGPU working group. And they came up with labels, among other things. And they are very useful, seriously very useful. You just have to name them well. So consider you have a code base with one small shader module, and you get this error. Wig-sol syntax in shader module at line 10. That's not so bad. We know exactly where to go. We just go to our shader module at line 10. Now consider you have a code base with 1,000 very large shader modules, and you get the error. Wig-sol syntax error in shader module at line 10. That's not so good. It's very difficult to know where you're supposed to be looking for your error. However, if it was something like this, where now we know it is exactly in our red triangle shader at line 10, much better. And once you have all your fundamentals, you can put them together and get some trippy visuals. It's lagging a little bit because it's just a QuickTime video running over and over in my presentation program. But this is an example of what you can do with fragment shaders. And that's the entire presentation. Congratulations for making it through. Hope you learned something. This has been From Magic to Mechanics, Demystifying GPU Programming. My name is Adam. I compiled a small list of resources that I think are good that you can access there. It's a README on GitHub, and there are socials if you're interested. Thank you for your time. You've been a great audience. Are there any questions? Yes?
You do parallel operations in the browser, and neural networks are very parallelizable. Does that mean you can start training neural networks in the browser?
So the question is that when you're able to access the GPU through your browser, can you then start training your neural networks in your browser? And can you do other things? So yes, basically I think you can, because you have full access. So it's probably going to be very slow because consumer devices are probably not the best fit for actually training neural networks. But you could imagine we're in a future where you go to some website and it asks to use WebGPU, and then it starts mining Bitcoin for you. So that's possible because you have access to these compute shaders. But a more interesting point of view with regards to neural networks that I've seen some people try to work on is to use it as inference networks. So if you have some neural network that you've already trained and your users may be privacy focused and they don't want to send all their data to your server in order to run inferences, then maybe you could have a web application that just gives them the model and then they use it on their own device. So that's one use case I've seen some people try to get up and running. Any other questions? Yes?
You mentioned for native that CUDA's like the go-to, or that your go-to. Is there a bit of a concern with NVIDIA, that being so NVIDIA focused, given how expensive NVIDIA GPUs have become, and it's a little bit difficult to get sometimes?
Yeah, so the question is if there's any concern about CUDA being a source of like vendor lock-in with NVIDIA being so dominant, expensive, and sometimes difficult to get. I think a lot of people are very concerned with it. The general take on that is that for now, it is probably the best place to go if you want to do anything related to machine learning, at least, because there's such a huge ecosystem of people that know how to do it, and it's so established. And I think it generally has a very good developer experience. But you do have some competitors in the field that are trying to like ruffle the feathers a little bit and and get their place. So an example is OpenAI released Triton, which they themselves at least argued is easier to get right than CUDA, and it demands less expertise. So I just want to check how we're doing on time before I take any more questions. Yeah, we have a couple of minutes left. Any other questions? I don't see anything. Then I'll let you leave. Hope you enjoy the rest of your conference. Feel free to grab me in the hallway if you want to talk some more. Thank you.